We're back looking at our socket 3 motherboard that we pulled out of this industrial PC case. It used to be a CNC machine, and in the last video we did take a look at the CNC hardware and the associated software. But in this video I want to see how well a 90s industrial computer, how well this can run some 90s games. So I want to run this in its stock configuration. Then we'll try and tweak the BIOS a bit just to see how much performance we can get out of it. And then we'll maybe try and throw a couple of upgrades at it. Just how well do you think a 90s industrial computer can run Doom, Duke3d or Quake? Now, like last time, we're not going to use the MDA graphics adapter that came with this. Rather, we're going to use a PCI VGA card. We'll just continue using the Matrox Mystique. We're going to need that anyway to run the games that I want to. We've got the original floppy drives still hooked up here, but you might notice this other cable now. That's because I've hooked up a hard drive, a quantum fireball, and period correct to this machine with its manufacture date of the 20th of March 1998. No games machine though would be complete without a sound card, and for that we're going to use this, the Zoltrix AV305, a Sound Blaster clone, but it does a pretty decent job. And then because of the games that I want to try and run on this, Doom, Duke3d or Quake, well, the 4 meg RAM that came with it isn't really going to cut it, especially for those two later titles. So we are going to have to increase that. I'm just going to remove that stick and we'll replace it with two matching sticks of 16 meg FPM. These are 60 nanosecond parts. Just use FPM memory for now because this module came out of it. This was FPM as well. But when it comes to upgrading this later, I do have a couple of EDO sticks that we'll put in it at that time. There was no cache in this when I got it, so we'll just leave it like that for now. But again, later on, we are going to introduce some. So just how well will this perform in its base configuration? And by that I mean, since there's no battery in here, it's just really sitting on the default BIOS settings. And in fact, in terms of those BIOS settings, one interesting thing that we discovered after the last video is that within the BIOS here, this thing defaults to always having two high density floppy disk drives. Drive A, 1.44 megabytes, drive B, 1.44 megabytes. But even putting that aside, if I just power it off here quickly and give it a problem, so for example, if I was to disconnect one of the floppy drives here, it's going to think that there still is a drive connected, within its BIOS settings, which usually would throw an error and cause the machine to pause on startup. But this BIOS seems to be configured so that it will just continue to boot. It did come up there with the message that drive B error, and it even said on the screen press F1 to continue, but I promise you I did not press anything, it just continued itself. And granted, it is just trying to boot to the hard drive because I have that connected now, but originally it would have been booting to its floppy disks. If anyone wants to take a look at the BIOS, I have dumped it along with creating images of the two original CNC disks, and I even dumped the ROMs of the CNC card. I'll leave a link to all of that down in this video's description. But we don't really need floppy drive B hooked up to continue our testing here. So within DOS version 6.22, because what else are you going to run? It's always DOS 6.22, isn't it? But what else would you use? But within here we have a games directory with 7 titles in there, but there's only 3 that we're interested in today. Doom S, Duke3d or Quake S. The dash S there is just because it's the shareware version. I just labeled it like that myself. So let's start with Doom. And as you might expect, we're going to be running the timedemo. So the command for that is Doom -timedemo demo 3. That seems to be the default one that most people run. So we'll just let it run through this. Now it does take a couple of minutes, so I will speed through it quickly just for your benefit. But already from what I can see initially here, it is having quite a hard time doing it. Now I have opted to keep sounds on. I know more so for a traditional benchmark you would probably turn sound off, but I want more real world figures out of this. How does it actually perform trying to run the games? If you were doing it, you'd want to play the games with sound, so that's the way we're testing it. So that has given us a result of 2,134 game ticks and 4,419 real ticks. To translate that into a frame rate, well, we take the 2,134 game ticks, multiply that number by 35, and then divide that total by the real ticks, 4,419. That gives us a result of 16.9 frames per second. That's an average frame rate. And just to try and explain what the game ticks and real ticks mean, well, Doom, the ID engine, is trying to run at 35 frames per second. The time demo forces it to render every single frame as if it was running at 35 frames per second. So time demo 3 that we ran there, it has a total of 2,134 game ticks, or essentially a total of 2,134 frames. In an ideal world, our computer would throw that onto the screen, 35 frames per second, and result in real ticks of 2,134. Our machine is running slower than that though, but because the time demo is forcing it to render every single frame, well, it took it a total of 4,419 real ticks to get all of that onto the screen. That's why you multiply by 35, divide by your real ticks. That's what gives you your actual frame rate, in this case 16.9. Maybe doesn't bode too well for the other two games that we want to try and run today. Although I do think there's a lot of performance left in this board, we will get to tweaking it later. The next game though I want to try is Duke 3d. Now, this game never came with a time demo or any benchmarking tools from 3D Realms, but YouTuber High Treason 610, well, last September he released his own time demo benchmarking tool for Duke3d. I'll leave a link to his video down in this video's description. Make sure you go and check it out and drop him a sub while you're there. I do think this will turn out to be a very useful tool for the community. Now to run it, you have to download his executable and associated files and just dump them into your Duke3d folder. It needs to be version 1.4, the Atomic Edition. That's what I have on here. And it's all just run from the command line. So it's Duke Mark. Then we need to specify that we want to see the statistics on screen and where on screen. BQ just puts them up in the top left hand corner. And then there's 3 benchmarks included. Bench 2 is the one that I think works best. And again, just like Doom, we're running this in a real world scenario, so sound is turned on. It's the numbers at the top there, they're the ones that we are most interested in. The purple number, that is the real-time frame rate, as in what it's generating at this moment in time. Red there is the lowest frame rate, green is the highest, and blue, that is the average. Now equally, this is quite a long benchmark, so I'll just skip through it for your benefit. See there, especially in this open area, that we are really struggling here. Definitely in the single figures. That's it finished, and we can see that our minimum was only 2 frames per second. We did hit a maximum of 24 though, but the average was just 7. Definitely pushing this little rig to its limit, although like I said, I do think there's plenty left on the table here. Next one then is going to be Quake. I expect this to be an absolute slideshow. I think the command to run this time is Quake, then plus timedemo demo 1. And again, just because this is running so slow, I'll just fast forward through it a bit. I expect this is going to take probably 5 minutes. One thing you might notice, by the way, is that just in there, I have put a fan on top of that CPU. It was getting very hot, like almost to the point where you couldn't touch that heatsink. Obviously, when this was in its original big case, the power supply was sitting directly over here, and the fan in the power supply would have been drawing air across the top of that CPU. We don't have that here, just the way it's all sitting open on the bench. So just stuck that fan in there just to help it a bit. Okay, it wasn't just as bad as I maybe thought it would be. We achieved an average there of 5.4 frames per second, which is definitely unplayable. In fact, I would maybe go so far as to say all these games have been largely unplayable. You probably could just about get away with Doom, but Duke3d and Quake here, you're definitely not playing them at these frame rates. Although before we try and do something about that, by trying to tweak this thing, I know some of you would probably prefer to see a proper synthetic benchmark. So we've got speed sys on here. And we'll just let this do its thing up to the hard drive test where it pauses. There we are, and I do think this has yielded some quite useful information. So on the top left of the screen there, we can see that it confirms memory size at 32 megabytes, but the memory bandwidth is only 58.02 megabytes per second. We can definitely do a lot better than that. Equally, just directly below that, it confirms that we have our Matrox Mystique, but the VESA memory, that's the graphics card's memory, its bandwidth, which is displayed in brackets there, as 13,475 kilobytes per second. That seems extremely slow, especially for that card. We then get a processor benchmark of 22.46, and then on the bottom right, that is our memory speeds. At the minute there is no L2 cache, just the L1, and you can see from the graph there, when it runs out of the 8K of L1 cache, that just tanks. Memory performance just drops off. So our data throughput on the L1 cache is 36.61 megabytes per second, whereas the general system memory throughput is just 19.57 megabytes per second. So what are we going to do about that? Well, the first thing that jumps out here is those empty sockets. And while yes, I do think that we could get some more performance out of this solely by tweaking the BIOS, I think the biggest performance improvement that we will see is by populating this with some L2 cache. So I have a series of chips here that we can drop in there, and this will give us 512K of L2 cache. But most importantly, these are 10 nanosecond chips. These are the fastest cache chips that you can get. or at least they should be anyway. Now granted, the Tigram chip, it's 12 nanosecond. I unfortunately couldn't find a replacement 10 nanosecond part for there, but even at that, I do think this should add quite the improvement. But we're not simply just going to fit that. I want to jump into the BIOS here and tweak a few things as well. So the first thing that I want to check in advance here is that the cache is all set up correctly. The internal cache, that's what's on the die, on the CPU, that's set as write through, and unfortunately we don't have any other option there, so we just have to stick with that. Write through is all we've got, but the external cache, that's set as write back. That's what I wanted to check. That's what we want. That is the faster of the two. We'll then go into chipset, and rather than have this thing configure itself automatically, we'll disable that. The DRAM read and write timings, well, that is the cache RAM, and because that is very fast cache memory, we're just going for fastest. Now the SRAM read timing, I dare say we may struggle to get this thing to boot at 2111, but we can try it. All we can do is try it. And in terms of SRAM write timing, well, 0 wait states is better than 1. Hidden refresh, we will turn that on as well. That basically allows the memory controller on the motherboard to refresh the RAM rather than taking up CPU cycles for the CPU to do it. Down in PCI then, and because we're running the Matrox Mystique here, which when we ran the synthetic benchmark, it seemed to be performing quite poorly. So let's turn on a few things here as well. CPU to PCI write buffer, will enable that, and we'll enable these two as well. We'll enable the DRAM buffer, but we'll leave palette snoop off, and I don't think we need to worry about IDE bus master. And you know what, just while I'm in here, I'm just going to turn everything that's on auto off auto, and we're just going to disable the serial and IDE ports. In terms of the onboard IDE, we're only using the primary IDE controller, and we'll just do a detect on the IDE, and we'll turn on 32-bit mode for the hard drive as well. Yeah, that's the way we want it. Will it boot though, since we have pushed all those memory timings? No. I think we've pushed things maybe too far. Right, it seems the only way I can get this thing to post reliably is with the 3222 SRAM read timings. Everything else is just exactly how we set it before though. And as you can see, it does now get us into DOS without seemingly any problem. I just don't really understand why we can't push that RAM further. We might have more luck when we switch that out to EDO. But let's just run our benchmarks again now, and let's see how much faster it is. So, Doom. And I think last time this worked out to 16.9 frames per second. Well, you can definitely see there from the results that it is faster because our real text is closer to our game text. But just how much faster is it? So we'll run through the calculation again. 2134 times 35 divided by 2780. That has given us quite the improvement. We're up to 26.86 frames per second. Almost exactly 7 frames per second faster. And that's just from adding the cache and tweaking those settings in the BIOS. Will it make Duke3d any more playable though. And certainly initially, yeah, that is a lot faster. In fact, judging by that average frame rate, it's almost as fast as Doom.
Damn, I'm looking good.
So I was hoping that the average might have held on to plus 20, but it hasn't. We have dropped to an average of 18 frames per second, still more than twice what it was previously. And certainly I think it brings that game into the realms of playability. But what about Quake though? I still think this is going to struggle. And yeah, a definite improvement. We're up to 7.5 frames per second now. Still not playable, and perhaps not as much an improvement like we've seen in the other two titles. But that is to be expected because, well, Quake is really looking for the Pentium. It's really looking for a fast FPU. There is one thing that we might be able to do to this machine. There is one upgrade we might be able to throw on it though to get Quake more playable. Before we look at that, let's take another look at the synthetic benchmark. And straight away there, the one that jumps out to me, in the top left hand corner, our memory bandwidth, well, that has exploded. More than doubled in fact. We're now at 126.79 megabytes per second. And equally, the graphics card, the VESA memory, its bandwidth, that has increased to 51,043 kilobytes per second. That's a massive increase on both those. Let's just see how the memory tests themselves pan out. Now that read test is very interesting. If you look at the graph of it there, again, it's super fast with our 8K of on-die L1 cache. And then it drops down, but doesn't drop as far as it did before when it's reading from the L2 cache. But when it runs out of the L2 cache after 512K, I would have expected that to further drop, but it hasn't. It's actually increased slightly. So how could that be? Does that mean that our RAM here is outperforming the L2 cache on a read test? I can't see how that would be possible. But in any case, there's our results. And again, across the board, it is considerably faster than what we were seeing previously. So what else might we do to this board to try and get a bit more performance out of it? Well, we can swap out that FPM memory for EDO RAM. I have 32 megabytes of said memory here. Now this is equally just 60 nanosecond RAM. I was trying to find some 50 nanosecond stuff, but unfortunately there didn't seem to be any out there. I'm sure it is quite rare, but 60 nanosecond should be fast enough for us. And then the only other thing really that we can change is the brains of the operation. We could change the CPU, and if we were going to do that, well, we may as well try and go for the fastest 486 CPU. But to change this CPU, well, it's the same socket, but it's not just as simple as taking this one out and dropping this one in. Rather, these two CPUs run at different core voltages. The original DX266 that was in there, that is a 5-volt chip, but the AMD that we're going to replace it with, the 5X86P75, well, that's a 3.45 volt chip, although it is tolerant from 3.3 up to 3.6. Now, I want this thing to run as cool as possible, so I want to try it first of all at just 3.3 volts. To change the voltage that goes to our socket here, we need to tweak a couple of jumpers. Now, that introduces its own problem. As we discovered last time, this motherboard, this is a US Logic Cardinal, but there's no jumper settings available for a US Logic Cardinal. Luckily enough though, over on the retro web, and with the help of a few people over on Discord, well, we found these two motherboards that certainly look identical. The Gemlite GMB46APS and the Ask Tech M1487-89 Rev B1. Both of those boards use the same chipset, and indeed the layout of both of those boards seems to be more or less the same. Although of the two, if we take a look at the jumper settings for them, or in particular just in terms of the jumper layout, well, it's the Ask board that seems to more closely match our board here, because just down at the CPU here, you would assume it is these jumpers that set the voltage, because that is the voltage regulator after all. That is the same as the Ask board, so it's that one that we'll pay attention to. If we just scroll down to this page, we can see the voltage settings. Now, this would have been set to 5-volt CPU. So, according to this document, JP13 would not have been populated, and that is correct. There's no jumpers on there. And then JPs 14 and 16, they would both be set to position 1, 2, and that is how those are set. So I am relatively confident that this will work. And to set this to a 3.3 volt CPU, we need to put 14 and 16 to position 2, 3, and then we need to put a jumper on JP13 at position 3, 4. That would be those middle ones. Before I go risking this chip though, and I don't want to tell you how much I spent on this chip, but let's just say it was reasonably expensive. Not only because it's an AMD P75, but because this is one of the latest chips, or one of the last chips produced, made in March of 1998. This is the BGC revision of it. And my hope there with this is that we'll be able to push this chip well beyond its factory specs. Although that's not for today. That's for a future video. Before I do go risking this in here though, I'm going to grab the multimeter and we'll just test one of the VCC pins on this socket, just to be sure that it's getting 3.3 volts and not something different that might fry this thing. So I'm going to have to test this on the bottom side of the board, as I can't get these into the holes in the socket. But if you bring up a pin out of the socket 3 from the underside, if I'm reading that correctly, beside this key point here, these two pins directly beside that, they should both be VCC. Then we can test them to a ground. And that's actually 3.45. Yeah, I thought that was meant to be 3.3. I think the difference is more than likely going to be on JP13 than anything. So in theory, if I move that to position 1 and 2 on that, according to our datasheet, that should make this 4 volt output. Let's see what it's doing. And no, that's 3.3 or 3.25 as it is there. And just for the sake of completeness, let's move JP13 into position 5, 6. Let's see what voltage that is. And yeah, 3.9. That's going to be 4 volts. So yeah, things are definitely different here than what I expected. But we'll set it to what we read as 3.3 volts anyway. Oh well, it was 3.2 something, wasn't it? And we'll just try this CPU like that. Okay. Does it work? Or does it go up in smoke? Please work. we're getting the video signal. Yep, it's booting. Although it's obviously forgot all our BIOS settings because there's no battery in there and power was disconnected for a while. But it has booted. AM 5x86, but processor clock 100 megahertz. That's not right. It should be 133. Now, we haven't changed any of the jumper settings for the CPU, and that's with a good reason. The way that chip works is that it runs on a 33 megahertz frontside bus, but when it sees a 2x multiplier, like what would have been set up for this CPU, 33 megahertz times 2 multiplier, 66 megahertz, DX2 66. But when that chip sees that, it's supposed to have an internal multiplier to take that 2 and multiply it by 2 again, basically making it 33 megahertz times 4, which granted is 132, but we just call it 133. What this might need is a BIOS update. So because this video is already quite long, I've decided just to omit this whole section where I'm screwing about with every BIOS I can find on the retro web. We did try quite a few, ended up just using the latest version available for the actual US Logic Cardinal. That turned out to be newer than the one that was already on my board. But I'm sure, as you expected, none of that made any difference. Rather, it's still a jumper problem, which I'm going to explain now. Well, it is many hours later, but we've fixed it. It now boots at 133 megahertz, and the problem was indeed jumpers. So, how did we figure that out? Well, went back to the retro web and found another motherboard with the same layout as this one. So the other board is the EDOM or Wintec MP060. And looking at the jumper settings for it, well, they are identical to this one. Remember when we looked at the jumper settings from the ASK board, there was a couple of subtle differences. All the jumpers were in the same location, but some of them were labelled differently. And in fact, the voltage jumpers, well, the pinout of them seemed to be different as we measured. Well, in this manual for the Wintec board, everything is exactly the same. And most importantly, in this, we scroll down to page 2, there are jumper settings for that processor, the AMD 5x86 P75. And that's how I did have it set here. But when I did have it like that, in fact, just let me switch it back to that quickly. It's just one jumper there, slightly different. That being this one here on jumper block J19. As you can see from the schematic in the manual, it wants that to be there. It wants those two to be there. Now, with it like that, it does boot at 133 megahertz, but the memory performance absolutely tanks. Well, you can see there that memory bandwidth is down to 87.5 megabytes a second. But more so, when it does this CPU test, well, that performance there is even worse than what we've seen with the DX2 66. And we can even see in this graph that the cache performance is abysmal. In fact, you can see there, once it gets me on the 512K of L2 cache, the memory speed actually recovers slightly. So it was running at 133 megahertz, but it was really, really unhappy. Once that test is finished there, that just again confirms that we're getting really poor performance on the memory. In particular on the L2 cache, its memory throughput is lower than the actual RAM throughput. So went back to that manual again, and if you look just above the section for the 5x86, well, there's two AMD DX4 CPUs there, an NV8T and an SV8B, and the only difference between those two in terms of jumpers is that one. Just at position J19 there, this one is moved. Now, the difference between those two CPUs is the type of cache that they have. The NV chip, as I understand anyway, has just write through L1 cache on die, whereas the SV chip, it has write back cache. much like our 5x86 does. But when I change that jumper setting, well, you might think that that would be forcing the L1 cache on our CPU here into a write through mode. But if we go into the BIOS, well, you can see there the internal cache is still set as write back. In fact, that's the only option that we have for it. If you remember earlier with the DX266, that internal cache was set to write through because that was the only option with our Intel chip. If we check SpeedSys now, well, our memory speed has recovered back up to 127 megabytes per second, and our CPU performance rating there, that seems to be correct, 49.65. That looks as if it's more or less exactly in line with what the AM5X86 should achieve. And then as per this graph, just giving us the memory timings, you can see that that has recovered as well. L2 cache is now over 34 megabytes per second, almost 35. That's more what we would expect to see. But just to confirm that the cache on this is indeed running in write back mode, well, on this disk here, I have put a couple more tools. We've got check CPU and cache check. So we'll run check CPU first, if I can spell. And that does confirm L1 cache write back mode. Just to be thorough though, we can run cache check. And okay, unfortunately this cache check has failed. I have found that before with that particular bit of software. If you have your DRAM timing set too fast, this tool, for whatever reason, doesn't seem to pick up the L2 cache. It only thinks we have the L1 cache, and it doesn't actually tell us there whether it's write back or write through. I thought this bit of software did. It doesn't though. CPU check though definitely did, and it definitely confirmed that the L1 cache was running in write back. And when we ran SpeedSys, that definitely showed us the L2 cache. We know that is also working fine. So we're doing it a wee bit back to front this time. We've run the synthetic benchmark first. What's the performance like in games? And it looks like it's flying along. Okay, this time our 2,134 game ticks only took 1,622 real ticks. So we know straight away we're running faster than 35 frames per second. But let's just run it through the calculator. So 2134 times 35 divided by 1622, just over 46 frames per second average. What about Duke3d? Last time when we tweaked the DX266, we got it to the point where Duke3d, you would consider it to be playable, although there was still a bit of stuttering. I wonder with this chip though, will it just be completely smooth? So far there, our minimum FPS is 30 and the average is in the 40s. Okay, granted the minimum's just dropped to 29, 24, 23. But if it can stay, I don't know, above 20, I think that will be perfectly acceptable.
Damn, I'm good.
Well, our minimum did drop to 19, but with an average of 37 frames per second, and the maximum peak there was 73. That definitely puts Duke3d into the realms of fully playable. I don't really think you would notice those couple of stutters where it drops down to, 19, 20 FPS. And certainly through watching the benchmark, it only seems to be at times where there's large explosions on the screen. So I want to call that very playable Duke3d, but what about Quake? I still think it's going to be a bit of a struggle, but let's just see how it gets on. Yeah, it seems to be when the lighting effects come into play. That's when you can definitely notice the stuttering. Otherwise though, it looks very smooth. At an average of 13, probably still just a little slow to call it fully playable, but I'm sure you could muddle your way through if you reduced the screen size. Just out of interest, and just for the sake of calling it a benchmark, what happens if we run it with no sound? I know we've been doing everything here today with the sound on because we want, a real world benchmark. But if we do disable the sound, we should see a slight increase in performance. And yeah, that lifts us to 14.1 FPS. Although, who's going to play a game with no sound effects? I suppose purely as a benchmarking tool, 14.1, but in terms of real world playability, 13. Either way though, still probably a little low to call it fully playable. So I'm pretty happy with what we've been able to achieve with this board today, but we're not finished just yet. There are a couple of things that I still want to try. This video though is far too long, so we're going to leave them for next time. And there's one thing in particular that I might need your help with. See the RAM on this, the SRAM? I cannot get this board to post with those read timings any tighter than 3222. If I try 3111 or 2111, it always crashes just at post. Any ideas? I've tried a couple of different sticks of 60 nanosecond EDO. I've tried changing the DRAM timings, tried slowing them right down to see if that might make any difference. But nope, it always crashes. So it just seems to be something with this motherboard. It just does not like those faster timings. Or is there something else I'm missing here? So if anyone has any thoughts on that, please do let me know. And then the other thing that I want to try, because this is the later version of the 5x86, we should be able to overclock this. It will mean playing with more jumpers here, and we may need to modify some of these jumpers that are factory set, with wire links on them. But it should be possible to push this chip to 160 megahertz by changing the board to a 40 megahertz frontside bus. And it may even be possible to push it further. I don't know, but it's something that I want to try. So make sure you're subscribed and catch that in the next part. Did you know that maybe 40% of the people who watch these videos aren't subscribed? So if you are one of those, and if you've made it this far into this video, why not hit that subscribe button? It genuinely does help the channel. I want to try and grow the channel. I need your help to do that. And the more people who are subscribed, well, that helps the YouTube algorithm push these videos out there to a wider audience. So if you would do that little thing for me, I'll promise to try and get every last ounce of performance out of this 486. But that's going to be it for now. Thank you very much for watching, and I'll see you next time.